Today we will start with the chilled water system design calculation. Okay, this is a new syllabus. So far we have seen air conditioning and the smoke management. Okay, today we will start with the chilled water system. Okay, in this chilled water system, if you see the syllabus, there is a chilled water introduction. Okay, then we have an architectural package which we have seen before. Then there are design basis report. Then HVAC room data sheet. Okay, there are different spaces. We will find out what is the thermal load. So based on that only, we will find out what is the total building heat load, and based on that we can design the chilled water system. Okay, then we have various codes and standards. Then we will talk about chiller calculation for the air cooled. Okay, then we have a chilled water pump calculation. Then we have another chiller called water cooled chiller when we use cooling tower. Okay, then based for that we require condenser water pump calculation also we will see. Then we have a cooling tower calculation and selections. Then we have a chemical dosing unit selection, pressurization unit and air separator, chilled water pipe sizing. Okay, then we have a various equipment schedule and selections. Okay, so this is the same procedure as a consultant. We go through concept design, schematic design, detailed design, and a tender package, and then IFC package as well. Okay, so this is the same similar syllabus for air conditioning and for the smoke management as well. Okay, in the same topic. Okay, so I will open one of the chilled water schematic. Okay, so when you go through this particular chilled water schematic diagram, okay, you can see there are a lot of equipments. Okay, in the chilled water circuit. Okay, so you can say normally in the chilled water system there are open system and there are closed system, right? So when you say open system, it is like you have a cooling tower, then you have a water cooled chiller. Okay, where the chilled water network is open. Okay, so that is open circuit. Okay, when you say that closed circuit, that it's a closed system, like starting from the chiller to the equipment, everything is a closed in between, right? It's everything within the system. Okay, say for example you have a chiller. Okay, then from the chiller you have a supply. You can say that chilled water supply line, which is goes to the building. Okay, directly, but through the pump, because you need a pumping device to pump the water from chiller to the building, right?
Yes.
So here basically you're rejecting the heat, and here you are actually absorbing the heat, right? So this is the chilled water network. Say for example this is a supply. It goes to the building. Okay, then it will absorb all the heat, then it comes back, then it goes to the chiller. So here it is rejecting and here it is absorbing. Basically it is the same like a refrigerant cycle. Is it clear? Okay, now
Yeah.
to make it circuit, what you are doing, you have a pumping system, right? So the pump, what it is doing, it is actually circulate the water from chiller to the building, and then it takes back from the building to the pump. Okay, sorry, to the chiller. So that is what the pumping interface is doing. Okay, so you heard about that there are two type of pumps. One is the building pump, and you can say another one is the primary pump, right? Okay,
Can I ask you a question if that's okay?
yeah, you can ask. Yes.
Yeah. So this one, what you're showing right now is the closed circuit, right?
Yeah, it is a closed circuit. Yes.
It is a closed circuit. So typically, closed circuit is when we have air cooled chillers, right?
Air cooled chillers. Yes, correct.
Okay. Okay.
Even if you have a water cooled chiller, also you have a closed circuit. Okay, I will tell you what it is. Okay, so water cooled chiller, you have a two side. One is the evaporator side and one is the condenser side, right?
Yeah.
Okay, so in the evaporator side, you will be having always closed system.
Okay.
Okay, in the condenser side, you have a two type of condenser. One is the air cooled, one is the water cooled. The condenser should be cooled, right?
Yes.
Okay, so that is one is air cooled, one is the water cooled. So air cooled means, say for example, when you go with the chiller, okay, you have a two type of chiller. As I said, you have a air cooled chiller. Okay, this is the air cooled chiller. So here you will be having evaporator, right? So in the evaporator, you will be having a chilled water return, you can say, okay, which comes from the building, and then it will be cooled by means of refrigerant, and then it will go to the building. So this is the chilled water supply and chilled water return. This is the evaporator, right? Okay. Now you can see there is a condenser. Okay, condenser is what? Say for example, if you go to the air cooled chiller, you might have seen like this section, right?
Yes.
So this is basically a condenser. Okay. Now here what it
That's the
is here.
condenser side of the entire chill within. So basically, what you're trying to say, in a closed circuit system, you would generally have your entire evaporator, condenser, all of the refrigerator, the typical refrigeration cycle components within one loop itself, so that you have only one set of line. I mean, like two sets of basically chilled water supply coming from one side, and then the opposite side you would have the return coming back to
Yeah,
the
written.
evaporator.
Okay. Now how this water will be getting cooled? That means you have a refrigerant cycle as well. Say for example, if I
Yeah.
if I if I draw like this, okay, I will draw
Mhm.
like this just for understanding purpose. Okay.
Understanding.
So
Yes.
so here you will be having a refrigerant cycle.
Mm.
This is same like say for example you have a DX, right? Say for example you
Yeah.
have a DX system. In the DX, what
Mhm.
you have evaporator and you have a condenser. Say for example you have
Condenser.
a DX unit. DX unit
Mm.
having inbuilt. Sorry, you have a indoor unit, right?
Indoor unit.
So
Yes.
indoor unit is you can call it as a evaporator,
Yes.
okay? And when you call it as a outdoor unit, you can call it as a condenser, right?
Yes.
So this is same like say for example, this is your evaporator which is inside, and this is the condenser which is outside. You can say like that, right?
Yeah. Yeah.
Okay. So this condenser basically rejecting the heat, and this evaporator basically absorbing the heat.
Mm.
Okay. So
Mm.
what here it is do what it here basically does. Say for example, this chilled water, it absorbs the heat from the each space, right?
Mm.
And
Mm.
then the supply temperature, say for example as a standard, the supply temperature will be 5.5 or 6 degrees Celsius, and it will go to the space, and then when absorb the heat, then it become like 14 degrees Celsius or 13.5
Mm.
degrees Celsius. So that
Yes.
13.5 will go to the chiller, right?
Yes.
So the chiller has to reject the heat. How it reject the heat? There is a refrigerant cycle.
Refrigerant cycle. Yes.
So this refrigerant will absorb all the heat from the evaporator. This
Mm.
evaporator again you can say like there is a evaporator. Say for example this is the evaporator, okay, and you will be
Mm.
having a two. Say for example you will be having a water will be passing through the say for example
Evaporator coil, and by
in
the
the
same time you
yeah
have the
in the evaporator there is a coil, okay, then also
yeah.
there is a refrigerant pass through, same like heat exchanger, okay,
Yes. Yes. So
so it
basically,
will
when the refrigerant passes through, like you said, the temperature exchange happens, and
yes
then
yes yes
because of which the refrigerant will pick up all of the hot water or high temperature.
yeah, it
The
will absorb
refrigerant
all the
begins at a
heat,
higher temperature. Yes, all the
yeah,
heat,
then it
and
will be
then
cooled, yeah,
yes, yes. The chilled water gets cooled, and the refrigerant picks up all the reject. I mean, like heat that
all the
needs to be
heat
rejected,
all
basically.
the heat, okay, so when that heat should be rejected, right? So that
Yeah.
heat rejection will happen. Say for example if you have an air cooled chiller, okay, so
Hmm.
this
Hmm.
whatever the outside air will take out all the heat from the refrigerant. Say for example you have a
Yeah.
condenser
Yeah.
fan, right? Say for example
Hmm.
you have a condenser fan on top of the air cooled chiller, okay, so when the
Yes.
condenser fan runs, it say for example the outside air, ambient air will go through the condenser, it will take out all the
Mhm.
heat, then it will reject through the condenser
Reject the
fan,
heat through the condenser itself.
okay. So this is the
Understood.
air,
Yeah.
this is the air cooled chiller. When you have a water cooled chiller, instead of this one, you'll be having another set of a heat exchanger, okay. So this heat
Okay.
exchanger, what will happen here, there will be refrigerant, okay. So instead of the air, what will happen, there is another circuit, okay, that is called condenser circuit. So where you have a
Okay.
condenser pump, and then you have a cooling tower, so that will be
Okay.
reject the heat by means of
Yeah. Yeah.
cooling tower.
Essentially, the thing is, within air cooled chillers, the entire refrigeration cycle is within one equipment, basically.
Yeah,
Whereas
yeah,
for water cooled chillers, you've got different, like each like condenser side is a separate equipment in itself, or condenser side of it. So that is the condenser pumps, the cooling tower, all of it is in one side.
yeah,
Whereas
yeah, yeah.
whatever that's being served to the building or the evaporator side is like another set of equipment, basically.
Yes,
Right?
correct. Yeah, yeah. Now, what is the difference? So say, for example, when you have a lower capacity, you can go with air cooled chiller. When you have a very large capacity, okay. Say, for example, as a standard, when you go with air cooled chiller, normally you have a maximum capacity like in the in the Middle East region. Okay, I'm talking about
Okay.
like
Yeah.
46-degree Celsius. You can go
Mhm.
maximum of like 1500 kilowatt, or maximum like 1550 kilowatt. Okay, so that is the maximum chiller capacity. Okay, okay. If you go with the, say for example, water cooled chiller, say for example you can go like say 3000 kilowatt or 4000 kilowatt or 6000 kilowatt, you can go in the water cooled chiller. So that means you can save the footprint. Say for example, you have a very large building. Okay, when you have a 10,000 kilowatt or 15,000 kilowatt building. Okay, instead of going with the air cooled chiller, you can go with the water cooled chiller to save the space. Okay, instead of 10 air cooled chiller, you can go with one water cooled chiller or two water cooled chiller. So
But
that is the
still, that
difference.
means you would still have to have extra space for the condenser cycle as well,
Yeah,
right?
yeah. But when you have instead of 15 chiller, okay, you can have some
Okay,
space for pump room. That is
Ah,
possible, right?
okay, okay, okay. So, but can you tell me the capacities once again? So, air cooled chillers typically, what capacities do you say? I mean, even TR would be fine with me. It's not necessary you have to. Yeah.
Basically, if you deal with a supplier, it will be normally in kilowatt. Okay.
Okay, okay, okay. Cool.
Okay. So as a standard, you can say in Middle East, you can maximum 1500 kilowatt,
Up to
1500
15,
kilowatt.
yeah, up to 1500 kilowatt. That's the
Yeah,
max.
is the maximum. Yeah, maybe you can go with some manufacturer. Maybe they can give you like 1600 kilowatt, or this is the range. Okay, more than that you cannot go. Okay. Also, if
Okay,
you go with the 1600 kilowatt, the length of the chiller will be fit into one truck for the transportation purpose.
okay,
If you go much
okay.
more than that, what will happen? The length of the chiller will be increased and will not fit
Hmm.
into the trailer, and the transportation will be very difficult. Or say, for
So,
example,
ba-
shipment. If you are
okay.
taking from outside country, okay, normally the ship having a container, right? So that will not fit. So that is why this also restriction based on that. That is one of the
So
factor.
basically, okay. So basically, anything typically 1500 is more like what manufacturers have in shelf, or is more like commonly used, or
Yeah, yeah, yeah,
what
yeah.
they're. But anything more than 1500 is more like custom built or
It's not
typically, right?
custom build. It's not custom build. Basically, yeah, you can say custom build also. You
Uh,
can request a higher, but the length of the
mm,
chiller will be very high, and
very high. Yes.
you have to see that architectural layout whether it fits into that or not.
Mm,
Okay,
mm, mm,
so
mm,
these are the
mm, mm.
parameters, but it's not that I'm not saying that it's stopped. Okay, you can go much
Yeah,
more
yeah.
that, but it
But yeah,
depends
but
on.
generally based on your experience in
Yeah,
the
yeah,
industry,
yeah.
you say you typically have used no more than 1500 kilowatts.
Yes,
Typically.
yes, yes, yes. Correct.
Cool.
Yeah.
Understood.
Okay.
Understood.
Okay, that is one of the factor. Okay, and you can say this is the chiller. Okay, then also you have a this is the your building site equipment. Say for example, fan coil unit or air handling unit. This is normally we have seen. So this
Mhm.
heat load, this capacity is based on the heat load. That is what we have seen in air conditioning, right? So you do
Yes.
the air
Yes.
conditioning thermal load calculation. Based on that, you will arrive at some capacity. Say for example, there is a 100 kilowatt. I'm just assuming.
Mm,
Okay, 100
mm,
kilowatt. You
mm.
have a say for example 15 building or 20 building or 20 spaces. Assume that you have a 2000 kilowatt, right? Or 3000 kilowatt,
Yes.
whatever it is.
Yes.
Okay, based on
Yes.
the building load. Okay, now
Yes.
based on that building load, you are going to have a chiller selections. Okay,
Mhm.
okay. Now this is the circuit. As I said, you have a chiller, then you will be having a building side equipment, cooling
Yeah.
equipment like AHO or FCO. Then you will be having a
Mhm.
pumping device. Okay, you have a chilled
Yes.
water pump.
Yes.
Say for
Yeah.
example, you will say building pump, and also you will say primary pump. Okay, the
Mhm.
primary
Mhm.
pump is normally required for the chiller. Okay, to make sure the chiller gets proper flow. That is why you have a primary pump. Clear?
Mhm. Okay.
Okay, so that
Okay.
is called primary pump. Okay, when you have secondary pump, this is called building pump. When you pump the water to the building, what is required? Say for example, you have a building, you have a very large building. So to supply from to all the area, okay, you require sort of like the pump head calculation, right? So you will be
Mhm.
supplying from all the way to the building, and then it circulates, then it comes back to the chiller. So that is what the building pump does, right?
One second, please. Yeah, sorry. Yeah, you were saying basically about the primary pumps and secondary pumps, right? Or the building side pumps, essentially. So, but the primary side pumps basically looks into everything to bring the water back to the chiller side, correct? Or
No, no,
the
no, no, no. The primary pump,
oh,
what it does, say for example, whatever the flow required for the chiller, okay,
yes.
because the chiller should run at proper flow. Okay,
Mm-hmm,
if you
mm-hmm.
don't supply, say for example, your chiller is running at full kilowatt, your chiller having what? You have a compressor, right?
Yeah, yeah.
You have all four compressors are running. Maybe if you go with the chiller selection, okay, you'll be having
Mm,
three compressor or four compressor. Normally four compressor, okay. or sometimes it go with 2 compressor, 3 compressor, depends upon the capacity. Okay, so when all the 4 compressor runs, that means it produces lot of energy, right?
Yes.
So that energy should be properly consumed. Okay, so when you run the chilled water flow, that chilled water will get all the necessary cooling from the refrigerant. Okay, so if you don't supply proper flow rate, but when the compressor is running, that means your efficiency of the chiller will go down, right?
Yes.
So to make sure that the primary pump will supply the required flow, what is required for the chiller.
Okay.
Clear, right? Say for example, if this chiller required 50 liter per second, okay?
Yes. Yes.
So this primary pump will make sure that it will take the network from 50 liter per second and it will supply to the chiller, right?
But
Okay.
this, but can I just request control here?
Yeah, you can question. Yeah.
Okay. I've requested. Can you accept? Have you? Okay.
Yeah.
So basically, what I wanted to ask you was, so this actually, what you're showing is actually the chill water return, right? Basically
Yeah.
coming from the building, right?
Yes, chilled water
So,
return. Yes.
so that means whatever that is going to the building, if it is 50 liters per second, say from one chiller, 50 liters per second on the supply side, it should come back the same 50 liters per second should come back to the chiller, correct?
Yeah. Yes. Correct. Yes.
Yes. So that is the function of the pump basically. Is that
Yes.
the
Correct.
case, or
Yeah.
is there
No.
anything else other than that?
See, what will happen, this particular pump will be variable pump normally because it's a building side pump, right? So the building side pump will be variable. Why it is variable? You have a AHU having consist of PACV. So the PACV will vary the flow rate based on the required demand, right? So when that varies, then what will happen? The flow rate will adjust. It will vary, right?
Yes. What typically what the worst case as per the building load, if it's 50 liters per second, due to the different orientation and applications of everything, AHUs, FCUs can go low speed, medium speed, or high speed. So typically your chill water can change, which will be controlled by your PICVs of the individual equipment in the air side, and accordingly your chill water gets fluctuated. So what would typically be 50 liters per second can become 30 or maybe 40, depending on the type.
Correct, right? So when the flow rate changes, what will happen? The chiller will not get sufficient flow, right? Say for example, the chiller, normally you can say there will be 6 chiller. Okay, normally you have a 5 duty chiller and 1 standby chiller, for example. Okay. So assume that 1 chiller is off and 5 chiller is running, right? Okay. So when the flow fluctuates, what will happen? That means there is no sufficient load there is no sufficient heat in the building. So that means you don't need to run all the 4 chiller, right? 5 chillers. So what will happen? Say for example, 5 chiller, it is like each chiller having 50 liter per second. So what will happen? You require 250 liter per second. Okay. So each pump will make sure that it will pump 50 liter per second. So this 50 liter per second to this chiller, and this particular pump will pump 50 liter per second to this chiller. Okay. So what will happen when the flow fluctuates? That means it doesn't get proper flow in one of the chiller.
No, it doesn't get. So basically, whatever, for example, if we say supply side only requires 30 liters, basically our understanding is the 30 liters should reach back the chiller, but that is not enough, right?
Yeah, not enough. What will happen? So that when the chiller required 50 liter per second, but it will supply only 30 liter per second, what will happen? The chilled water temperature will get cooled quickly, right? Say for example, the chiller is running at high full efficiency, but when there is no proper chilled water flow, what will happen? The temperature quickly it gets cooled, right?
Yes.
Okay. So what will happen after some time? It will get say for example, you have a 14 degrees Celsius, and here it is 5 degrees Celsius. Delta T will be 9, for example. Okay. So what will happen? Because of the lesser flow, this will start cooling overcooled. Like it will become 3 degree and say for example 2 degree. Okay. So it will start go down. But what the chiller will try to maintain, it will try to maintain the delta T. Okay. So when it try to maintain the delta T, when it can't try to maintain the delta T, what will happen? The chiller will become step down the compressor. That is the first step. Okay. So that is the first step. Still, the chiller can't function. Like the chiller can't reduce the delta T. What will happen? One chiller will be turned off and the other chiller will be work at required speed.
Yes. Yes.
Clear, right? So
Okay.
the properly the flow will be adjusted. So if I say, for example, you have a instead of 250 liter per second, you have only 200
Mm-hmm.
liter per second. So that means only like the four chiller will be running. So one chiller will
Okay.
be shut down. So still you don't have any demand. There is no load.
Hmm.
What will happen? The
Hmm.
next chiller
Hmm.
will be turned off.
But then, but this is my, but this entire 250 that we're saying is for the entire site, right? It's not for one building alone, right? Or based on your example, is that the case? Or when you said
No,
these
see
five chillers?
when you design five chillers for one building, right?
Okay, yeah, okay, understood. Okay, my mistake
Okay,
then.
no,
It was my mistake.
yeah,
I think
yeah.
I took it in
See,
the
when
wrong
you
way.
multiple building, that is called your tabri, like district cooling plant, right?
District cooling plant. Okay. I
Yeah,
think
that
I went with that analysis. My
yeah,
mistake. It's
that
my
is a
mistake.
different. But whenever you go with, say for example, you have a residential building. When you
Hmm.
go with the high rise tower, you decide with one chiller. Okay, you can see as a building owner can decide anything whether he can go with the a district cooling provider or he can go with the air cooled chiller. Okay, so that analysis can be done by consultant. Okay, how the energy analysis, which is cheaper. Okay, sometime if you go with a third party, you will be paying based on the TR or based on the kilowatt. Okay, but if you go with the own air cooled chiller, you have to maintain air cooled chiller. You have a lot of cost, right?
Yeah.
So these all the things they have. You have to see. Basically you have to decide what is the best uh,
Option.
option to decide. Okay, that is based on
Decide.
the kilowatt and based on the locality also. Say for example, if you go with the uh, like say for example in uh, what do you say like
Maybe Dubai,
downtown area,
maybe
Dubai
like
downtown
outside,
area.
like outside, maybe
Yeah,
Alain or Ras Al Khaimah, where we don't have chill water or DCP or anything. In
yeah.
that
That
scenario,
then
we will have to.
you can go with the building, or you can go with the say for example in the building. Okay, there is no
Yeah.
proper space.
Hmm.
Okay, something like that. Okay, but if you see one of my project where you have a network is available, but still the owner gone with the own air cooled chiller. Okay, that is also his decision.
Okay. Hmm. Hmm.
So that is one of the factor. Okay, so this is
Yeah.
the basic as a chilled water network. Okay, then in the chilled water
Hmm.
network typically you will be having air and dirt separator. Okay, so this
Yeah.
will take out.
Before we go to that section, can I just go back to that? I've just got a couple more questions.
No
So,
problem. Yeah,
like
yeah,
you said, so basically, based on our example right now, we have around like six chillers, of
yeah.
which five is duty, one is standby. Correct?
Yes,
Yeah.
yeah,
Yeah, and we've assumed that each of them is like 50 liters per second. So basically, our capacity is 50, 100, 150, 200, 250. That is the ultimate duty, what we're trying to say. The
yeah.
the chillers, air cooled chiller system as a whole is providing 250 liters per second to the building side. Okay. Now, in this scenario here, just correct me if I'm wrong. This is what I've understood. Say, for example, our one of the buildings, or like in not one of the buildings, certain floors are not like working up to full capacity. So that means your building side chilled water drops down. So in this case, once the return comes back, what say if it's 30 liters per second in one of say in chiller one, and now that 30 liters comes back here. You said there is going to be a scenario where the cooling can become faster, or the cooling will go even lower, because what you might whatever delta T that you said will go even lower, right? So why is that happening? What is this? Can you tell me the basics behind that? Am I making sense? Or
Yeah. See what
yeah,
I'm saying. See, for example, you have a equation. Okay,
mm-hmm.
like a Q equal to MCP delta T, right?
MCP
For
delta
example.
T.
Okay,
Yeah,
so
yeah.
the heat and the flow should be proper, right? Say for example, Q equal
Yes.
to MCP delta T, right? The for the proper heat transfer.
Because based on that formula, if you look at it, delta T is proportional to the flow rate. So that means the high. Oh, you mean lower the flow rate, lower the delta T, basically. That's
Yeah,
the
delta T,
outcome.
right? Like
Yeah.
the lower the flow. Say for example, if you lower the flow, your I can say
Delta T
that
is also reducing.
yeah. No, see what I'm saying. When you say delta T will increase, right? When the flow reduces, delta T will increase,
No,
right?
what I meant to say is if it's 30 liters per second, what your typical delta T would have been 9 at 50 degrees would be maybe 3 degrees or 4 degrees, correct?
No. See, what I'm saying, Q equal to MCB delta T, right? Basically, basic
Yes,
equation.
yes,
Okay.
yes, yes.
Do you agree that when the flow reduces, the delta T will go up?
No,
When the flow reduces, delta T will go up, right?
it
To
should go
make it
down, right?
Q,
Because it's directly
no,
opposite
say,
from that.
no. See, for example, 10 equal to 5 into 2, for example, right?
Yeah.
So when you reduce the 5, that 2 has to increase to make it 10, right? 10 equal to 5 into 2.
Ah,
The 5 is 10 is constant.
oh, sorry. My mistake. I think, yeah, okay. I understood where I was making mistake. No,
Yeah,
I understood what you're talking.
the
Yeah,
similarly the same thing will happen when you reduce the flow.
yeah.
Delta T will increase, right? For
Yes,
example,
yes.
when you say 14 degrees Celsius will
Hmm.
should be 5 degrees Celsius, right?
Yeah.
But what will happen? The 14 will become 5, 3, 4, 3, 2, 1 because the flow is less.
Hmm. No, I understand where you're coming from. I
Clear,
understand.
right? Okay.
Yeah.
So now
Yes.
you have to maintain delta T. Okay, because the chiller
Mm-mm-mm.
cannot go. Why it cannot go lesser temperature? What will happen if it goes less temperature? Can you answer? For example, when you go more delta T, what will happen? How it affects the chiller? For example,
Mm, that means I mean, whatever the chiller will get overburdened, right? Because whatever cooling coil you have set within the chiller, that's the temperature that it wants to maintain consistently, right? Or is
yeah,
that
that is
true? Or
okay. I will tell you some more thing. What will happen if it goes to 0 degrees Celsius? Water
it freezes, it becomes zero.
freezes, right? So that will affect, that
Yeah.
will damage your coil.
Yes, it will damage the coil. Yes.
So that is what we are going to maintain the delta T. That is one of the very important factor.
Okay.
Okay, clear, right? So that is the first step.
Mm-hmm.
Very, very important that one. But you have a sometime you have a flow switch and also you have a freezing protection inside the chiller. When you go and read
Okay.
the specification, you'll be having
Mm-hmm.
important point. Okay, you cannot run the chiller without flow. That is one of the factor. Okay. Then
Okay.
second one, you cannot run with the chiller with the 0 degrees Celsius. That is one of the factor. So these are the factor.
Mm-hmm.
So that is why the delta T is very important. Okay. So when the delta T
Okay.
goes increases, then what will happen? Your chiller will start trip automatically, or sometime it
Not
will
automatically.
switch off automatically. Okay.
Mm-hmm.
So that is the
Okay.
main, that is the main. Okay.
Mm-hmm.
And if you increase the delta T, what is happening? Your basically, as you said, it's burden because chiller it is required only 5 degrees Celsius, but it is working more what is required, right? More than what is required,
Mm-hmm.
which is not required, and that means you are consuming more energy.
More energy.
Yeah, which is not required. Okay, so that is all. These are the
Mm-hmm.
factors. Clear, right?
Understood. I understood. Yeah. Now I've
O-
understood. Yes.
Okay. Now the chiller, the water is going to the building by means of chilled water pump. You will say normally
Mm,
building pump. Okay,
mm,
because this is
mm.
working as a building pump. This particular
Yes.
building pump normally it is a variable drive. Because why it is variable
Okay.
drive? You'll be having a TACV.
Yes.
Okay, but if you go with the three-way valve, you can go with the constant speed drive, right?
Three-way valve. I'm not really sure. Variables.
Yeah,
So
there are
basically, if it's yeah.
there are two type of valves for the
Yeah.
control. One is a two-way valve and one is the three-way valve. But normally, two-way valve is simple. Okay, simple in
Mm-hmm.
construction and simple, simple. You can say philosophy. Okay, instead of three-way
Okay.
valve. Three-way valve is very
Yeah.
complicated in construction as well. Okay, so if you go to any
Mm-hmm.
of the project, no one uses three-way valve. Okay, they use
Okay.
two-way valve. Okay, so what does two-way valve? Remember, we had a discussion about the PACV, how it works, right?
Yes.
Okay, so basically, whenever there is a demand, it works. It will supply the required flow. Okay.
Yeah.
So then what will happen when the flow when the particular building achieve the particular demand? What will happen? The
Mm-hmm.
flow will not go
The flow
right.
will not go.
It will
Basically.
stop. It
Yes.
will stop. So that
Yes.
means
Yes.
it will try to reduce the flow. So it will try to pump more flow, but the return will be lesser flow. What will happen? Correct. Okay. Now that what will happen? The pressure will build up here,
Yes.
right? So that pressure,
Yes.
there is you heard about delta P sensor in the line. Okay, pressure sensor basically. Okay, so what will happen? This particular pressure sensor will have a signal to the pump to reduce the speed, so that it will try to
Okay.
maintain the speed based on the flow.
Okay. So, but then this is only in the case of your three-way, if it's in a three-way valve, right? Or three-way valve scenario.
Three-way valve means you are bypassing the entry flow, right? Say for example, you have
Okay.
100 liter per second you are supplying, and only
Yeah.
you require 50 liter per second. That means the 50 will be bypassed. But as a return, you will get 100 only. So that means you don't need to vary the pump speed, right? But here it is what is happening in the PSEV valve, two port PSEV valve. What is happening when you pump 100 liter per second, but it is required only 50. It will take out only 50 and it will try to stop that 50. Everywhere it will try to stop. So when it try to stop, what will happen? The pressure will creating here in the supply line,
main header
in the header line. Yeah, basically yes. So what will happen when it tries to increase the pressure? Then there is a pressure sensor will try to reduce the pump speed to maintain the proper pressure.
Yeah, understood. I understand. So, but this pressure, along with the PICV, both in the air side equipment and even in the water side equipment, we will have like these sensors as well. Not just it doesn't work along with only with the valves. It also requires the sensors and everything, right?
Yeah. Of course,
cool,
without control system, it cannot work.
Cool. Understood. I think I've understood. Yes.
Clear, right? Okay. So what will happen when you have a lesser flow will come into the chiller, right?
Yeah, it will come to the return line.
Yeah, when there is a lesser flow, that means it will try to check like whether the first chiller is pumping 50 liter per second, second is pumping 50 liter per second, third is pumping 50 liter per second, but fourth doesn't have enough water, right?
Yeah.
So then it will go to the chiller. Then that particular chiller will try to sense what is the flow and if the delta T can maintain or not maintain, then it will try to reduce the compressor speed to maintain the chiller flow rate and the chiller temperature. Still, if it can't, then what will happen? The chiller will be going to switch off mode. Okay. Clear, right?
Okay.
Then the other chiller will be
other chillers will be working.
To satisfy the building requirement, right?
Okay. Understood.
Okay. Then if you go further down, then apart from this chiller, primary pump, secondary pump,
building side pump,
then you have a building side pump. Then you have a equipment. You have additional devices, additional equipments where you can see there is a air and dirt separator. Okay, so whatever air in the system or dirt in the system will be taken away by means of air and dirt separator, right? Okay. Then you'll be having a press.
Or
it's a single equipment.
Okay.
The water will pass through the air and dirt separator.
Okay.
And then say for example you have a automatic chemical dosing system. Okay. Say for example you want to maintain the chilled water properties, right?
Okay.
The water properties. Okay. The water properties can go up and down because of the ion components. Say for example you have a chilled water, right? So the chilled water internal you have a ion, right? So steel material. So that can mix with the water.
The chilled water pipe in itself. It's a great.
The pipe. The pipe. When the water pass through the pipe, what will happen? There is erosion on the surface, right?
On the surface, yeah.
So there is a particles. The small particles can be it can damage the pipe, and that particular particles will be mixed with the water, right?
Yes.
Okay. Slowly, it is not a much. It will have a small component. Okay, like small particles. So, but when you have an entire system, that when you add up all together, it will be large particles, right? Okay, so that particular ion, when it having ion, so that particular ion, or you have a water consists of salt, right?
Yes.
So the salt will deposit, and the salt will become like a stone after some time. Same like our body, right? Okay, so that stone will go to the coil, so that it can damage the coil, right?
Yeah.
So that is why we have a air and dirt separator to remove all the whatever the gases inside and whatever the dirt inside. Okay, then you have automatical chemical dosing and manual chemical dosing to make the chilled water properties healthier. Okay.
Okay.
And then you have a pressurization unit. Say for example, you'll be having a expansion and contraction in the chilled water itself. Depends upon the temperature and on all if there is any leakage in the system. Okay. Okay, so what will happen? You have to have a makeup water, right? So that makeup water will come from the domestic potable water, and then you will supply the water into the system by means of pressurization pump.
Okay.
Clear, right?
But that will be in a different temperature, right?
Yeah, but it will be very low, small water, right?
Okay. It's not very massive. Okay.
Yeah, and also you are going to mix with return temperature only, return water. Okay, return water temperature, say for example, 15 degrees Celsius. Okay, so that will be going through the chiller, right? So it will be cooled. It will be cooled automatically.
Okay, you mean to say even though if it's even if it's at a higher temperature due to the small amount or anything, and because of the larger amount coming from the return side, you just manage with it, like how we
Yeah,
mix
yeah. It will
hot
not
water
have
and
it.
cold water, like how we do it. Okay,
Yeah, yeah. It will
understood.
not make something different. Say for example, you have a
Different.
10,000 liter water, and if you add
Hmm.
2 liter water, what will happen? Nothing will
It will
happen,
not
right?
It will not. Yeah, yeah, understand.
Okay,
Also,
okay.
one more question here. In
Yeah.
the automatic chemical dosing plant, you have shown the supply and the return line. But whereas with the air and separator, it's only the return line that's being shown, or
No, no, no. This is
will
all
there be?
return line only. This is all. Say for example, this is all return only. Going to the building, right? See, this is the chiller part, right?
Yeah, but then if you see here, you've seen the automatic chemical dosing plant, your pot. In that, you have actually shown a supply line from the header that's going that side, and then the return also going back. That's why I was asking.
No, no. This is not exact. This is just a schematic.
Ah,
Normally,
okay, okay.
it will be connected with the return only. Okay.
With the
No need
return
to get
only. Okay.
confused with this one.
Ah, okay, okay, okay.
Okay, that we will see in between in detail, one by one component in
Yeah,
detail,
sure,
so that you
sure,
can
sure.
understand each one. Here, see here there is no much calculations because the calculation part we have already seen how to calculate the thermal load, right?
Yes.
Okay, here basically what we are going to see how the each and every equipment is being selected. Okay,
Mm-hmm,
that
mm-hmm.
basically based on that only we are going to have classes, right? Okay, now you have already calculated thermal load. So based on the thermal
Yes,
load, you are going to select the chiller based on that
yes,
capacity. Okay,
yes,
so how
yes,
you are going to
yes.
select the capacity that we will see one by one, right?
Okay, yeah,
Okay, see now what I request, I think now it's almost 45 minutes. What I request,
yeah.
I will share one document. Okay,
Okay, yeah,
this particular document, like you can say chilled water complete set, I will share it with you, right?
yeah. Sure,
Okay,
sure.
okay.
Yeah.
In that, if we have a time, okay, what you can do, if you go to chiller calculation,
Mm-hmm.
uh, say for example, you have a chilled introduction to chilled water system. Say for example, okay,
Yeah,
in this
yeah.
particular one, you can go through if you have a time
Mm-hmm,
just
mm-hmm.
read what you can this is about introduction to chilled water system when you have a time, okay,
Yeah,
then
yeah.
you can see this particular item HV system,
Mm-hmm,
okay,
mm-hmm,
and you can go to the chiller part, okay, here you can see
mm-hmm,
the centralized air conditioning system where you can see the
mm-hmm,
chiller, right?
mm-hmm, mm-hmm,
Okay, you can see that pumps, chiller, FCU, AHU, you can see, right?
mm-hmm,
Diffusers,
mm-hmm, mm-hmm.
okay. Then
Yeah,
transport
yeah.
system is nothing but piping and ducting.
Or
So ducting
ducting
diffuser
for air.
is for the
Mm-hmm.
air cooled air side, and
Yeah,
normally the other one for the
water side.
water side. Okay. Then you can talk about air conditioning equipments. Like you can know about chillers. If you have no
Yeah,
need to read everything, just have a glance. Okay. You
yeah, yeah.
cannot read.
Sure, sure.
It's very difficult to read everything. And then you
Yeah,
can
yeah,
talk about air cooled chillers, type of chillers, air
yeah,
cooled chillers.
yeah.
Okay. Then you have a water cooled chillers. How this circuit, right?
Mm-hmm.
Okay. Then you have a constant flow chilled water system, full load condition, off load condition.
Okay.
Okay. Primary, secondary distribution scheme, right?
Mm-hmm. So this
Okay.
primary
Then
secondary is basically the primary, the what we discussed in today's
yeah,
class, right?
yeah, yes, yes, yes. Primary side and secondary side. Okay.
Yeah, yeah.
Okay. Doesn't mean that primary is one type. There are multiple types of that. When you say primary, say for
Mm-hmm.
example, you have a Tabrid side, Tabrid building, right?
Yeah.
In the Tabrid side, whatever the water comes from Tabrid to the building, there is one pump.
Yes.
That is called primary pump. You can say.
Okay. Yeah.
So when there is a building side, you can say building pump or secondary pump. Okay.
Secondary pump.
Okay.
Mm-hmm.
Then you can talk about chillers here, water cooled chillers, right?
Mm-hmm. Mm-hmm.
Then you can talk about the components, like just have a look, glance on compressors. Okay,
Yeah,
then
I wanted to ask you these components and everything, Bunny. How important is it for us coming from a consulting side of things? Is it
see
really
consulting side,
important?
the compressor basically different compressor give you different efficiency.
Okay.
Okay,
Mm-hmm.
normally you will go see. You cannot say that all the compressors are good, all the compressors are bad. It's not like that. Okay, depends upon
Yeah.
the capacity. That particular compressor will be good. It will be good,
Good. Mm.
good efficiency. Okay,
Yeah.
so that is depends upon the flow rate or depends upon the efficient like a capacity. Everything that particular compressor it works. Okay, but all compressors are good at that particular capacity. It's like that.
Yes. Yes. Okay. 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 So
Okay.
it's not necessary that we have to know what type it is, but generally when we communicate, it's based on our communication with our manufacturer basically to understand what is better, what is not better, which is efficient, and like
Yeah, see, actually speaking, I will tell you frankly that who will
Mhm.
educate us is is a manufacturer. Okay.
manufacturer.
Yeah, they are only will tell us what is best, what is a good one because they are doing the research, right?
Research behind it.
Oh,
Yes.
okay. So basically, if you are a consultant, we deal with the manufacturer. Okay, but if
More.
you go with the
Yes.
contractor, they deal with the dealers or who is the suppliers basically.
Mm,
But we deal with
mm,
the
mm,
manufacturers, right? The
mhm,
manufacturer
mhm, mhm.
will tell us that what is good, what is bad based on their based on their research. Okay,
Yep.
so they are the
Yep.
one who educate us basically. Okay, they are the
Yep.
one who help us to create the specification.
Mhm,
Okay, but
mhm.
normally what we do, we compare with the three, four manufacturers and we will try to judge. Okay, and then
Yes.
we will apply on our specifications because some manufacturer will try to, play on their side, right?
Mm,
So that we have to judge
understood. Yeah.
between two, three vendors and then we will try to write our specification. So what we do normally when we are working with a project, we do the calculations, then we prepare our schedule, then we send with a different manufacturer, right? Okay,
Yeah.
so different manufacturer normally what you need, you have to uh, select the basically you require power, you require sizes of the chiller, right?
Mhm,
Then
mhm.
you require different details. Okay, so that you will send the details to the four manufacturer and you will try to get all the information. Then you will try to validate all four. Then based
Yeah.
on that, you will try to write your specification. Okay,
Got it. Understood. Yeah.
so that is the one. Then here you can go through the compressors. You can go through
Mhm.
auxiliary items like fans. You can say the pumps. Then pump having different pump, horizontal centrifugal pump, vertical centrifugal pump. Okay,
Mhm,
different pumps. Okay, you can see that pumps arrangement, right?
mhm, mhm.
Okay, then I think this side you have air side. Then you have a controls, say expansion tank, control valves. Okay, thermal storage, right? You can just
Yeah.
have a look, just to get idea only. Okay, then
Yeah. Yeah. Yeah.
I will give you different documents to you to read. Okay,
Yeah. Yeah. Sure. Sure.
because in the chiller part,
Mhm.
it's more document to read. Okay, rather than speaking, right?
Okay. Okay.
Okay, I will
Understood.
be
Understood.
sharing
Yeah.
many documents like go through the basic things. Then I will tell you that what is required for the chiller. Okay,
Mm, mm,
there
mm,
are
mm.
many chilled water guides. Okay, for you to
Mhm,
read.
mhm,
I will be
mhm.
sharing one by one
Sure.
to get some knowledge. Okay,
Get used. Yeah. Yeah. Get.
there are many documents are available, but I want to
Yeah.
share step by step. Okay,
No. No. Yeah. Yeah. Let's go one by one. Yeah.
yeah,
Just go
yeah,
ahead.
yeah. Okay,
Yeah.
Elvin,
Yeah.
I will just stop recording. Okay.
Yeah. Sure. Sure.